Dear students, greetings of the day. This is in continuation to our previous lecture, numerical solution of ordinary differential equation. We will discuss Euler's method, then the modification of Euler's method, and then at last we will discuss Runge-Kutta method. Euler modified method is a iterator method where Euler and Runge-Kutta methods are direct methods. In this lecture, we will discuss numerical solution of ordinary differential equation using Euler's method. And we already discussed two methods in my previous lecture, and for Taylor series method and Picard's method of successive approximations. As we see, both the previous methods are based on power series method. Now here we describe a method which is based on tabulated values. So Euler method is the first method in this category. We want to solve a ordinary differential equation dy by dx equals fxy with initial conditions y at x naught is equal to y naught. So as we already seen in the previous methods that we have substituted the power series of this function, but here in Euler's method we assume fxy equals fx naught y naught in first interval x naught and x1. Then we get y1 approximately equals y naught plus, now fx naught y naught is a constant term, so it can be written outside. So we are left with integration x naught to x1 dx. So that is x, so putting the limits x1 minus x naught, that is the differencing of the interval, and its value is h. First interval means solution of y at x1 by Euler's method is this. Similarly, we will get solution for x1 to x2, y2 equals y1 plus h fx1 y1. So continuing like this, we get yn plus 1 is equal to yn plus h fxn yn for n 0, 1, 2, 3, so on. So this is called Euler's method. Let us now discuss a numerical based on Euler's method. Initial values 0 and 1, and we let common differencing is 0.01. So next is 0.01, 0.02, 0.03 and 0.04. And we name them. This is x0, x1, x2, x3, x4. Corresponding y0, y1, y2, y3, y4. So this is the answer which we are desired to find, but to reach this we have to go through all these steps. So at step 1 we will get y1. So using Euler's formula, y1 equals y0 plus h fx0 y0. So putting the value as fxy is minus y, so fx0 y0 is h of minus y0, and y0 is 1. 1 plus h is 0.01 minus 1, so which comes out to be 0.99, right? 9606, 0.9606. So which is the desired answer? The solution of the differential equation at 0.04 is 0.9606. So method for solving ordinary differential equation is modified Euler method. So as we discussed the drawbacks of previous method, Euler's method, that for accuracy in solution we need to take smaller value of h. So here is another modification to that method. So the differential equation that we are going to solve is dy by dx is equal to fxy with initial conditions y at x naught is equal to y naught, and integrating both sides we get y1 equals y naught plus x naught to x1 fxy dx. And by Euler's method, the solution in first interval is y1 is equal to y naught plus h f x naught y naught. Now here, instead of replacing fxy by fx naught y naught, we will substitute the value of this integral by trapezoidal rule. That is x naught to x1 fxy dx equals h by 2 fx naught y naught fx1 y1. Here you will be surprised to see that we are calculating y1 and we are using y1 here. So this y1 we will get from the previous method, that is Euler's method. And first we solve the numerical using Euler's method. The solution we get, we will take it as a initial approximation to the solution, and that solution we use here. The modified method becomes, the first approximation to the solution is y naught plus h by 2 fx naught y naught plus fx1 initial approximation to y1. So similarly, second approximation to y1 is y naught plus h by 2 fx naught y naught plus fx1 y1 1. So we keep on repeating this until we get the desired accuracy. So we can write y1 n plus 1. N plus 1th approximation is y naught plus h by 2 f of x naught y naught f of x1 y1 n. So this is the Euler's modified method. Now to better understand this method, we will discuss a numerical. So again, this is a tabular method, and we start with the table. So first of all, we make the steps. So this is x and y, and these are the initial values. So we let h is 0.05 and this is 0.1. We name the points x0, x1, x2. This is y0, y1, y2. So actually we need to find y2, but before that we have to find y1 using Euler modified method. So as we already discussed, we start with Euler's method to have initial approximation y1 0, that is y0 plus h f x naught y naught, and here h is 0.05. So y0 is 1, h is 0.05, and x square plus y, x is 0, that is 0, plus y is 1 square, that is 1. So we get 1.01. So this is the initial approximation. Now the first approximation to the solution by Euler's modified method, y0 plus h by 2 f of x0 y0 means x0 square plus y plus f of x1 y0 0 means x1 square plus y1 0. So 0.05 square, and now instead of y1 0 we just replace with this 1.0513, and after calculating this comes out to be again 1.0513. So as the two iterations are same, so this is the solution for y1. Now second step, we need to find y2. So again, to find y2, first we have the Euler's method. By Euler's method, y2 equals y1 plus h f of x1 y1, approximation to y2, that is y0 y1 plus h by 2 f of x1 y1 f of x2 y2 0. To substituting all the values y5 1, and after solving you will see this will again comes to be the same. So these two are same, so the solution is 1.1055. Hence the desired solution of differential equation is 55. Runge-Kutta method, so which is again the modification in Euler's method. So we start with the ordinary differential equation with the initial condition. Integrating both sides, we get y1 is equal to y0 plus x0 to x1 fxy dx. And here again we replace this y1 by Euler's method. That is y1 is equals y0 plus h fx0 y0, and we will substitute here fx0 y0 as f0. So it becomes y1 is equals y0 plus h f0. So substituting this value here, we get y1 is equals y0 plus h by 2, this is again f0 plus f of x1 is x0 plus h and y1 is y0 plus h f0. And again we substitute k1 is equal to h f0, so it becomes y1 equals y0 plus 1 by 2 k1 plus h f of x0 plus h y0 plus k1. So this is h f0, which is k1. So we further write this as y0 plus 1 by 2 k1 plus k2, where k1 that we already know h f0 and k2 is h f x0 plus h y0 plus k1. So we solve this by Runge-Kutta's second order method. So by that method we let h is 0.1, and by this method the formula is y1 equals y0 plus 1 by 2 k1 plus k2, where k1 is this here, y1 will comes out to be y0 2 1 by 2 0.2 plus 0.21. So solving this will comes out to be 2.2050. So this is y at 0.1. To get second part, again h is 0.1 and the formula becomes y2 is equal to y1 plus 1 by 2 k1 plus k2. First solution at 0.1, second solution at 0.2. This we already calculated, this is 2.2050. Now to find this solution, now the initial values are these values. We make use of this because here this is x0, x1, x2 and this is y0, y1, y2. So we substitute here, k1 is h f x1 y1 and k2 is h f x1 plus h y1 plus k1. 105 plus 22155, and after solving this will comes out to be 2.4210.